Design for manufacturability is the general engineering art of designing products in such a way that they are easy to manufacture. The concept exists in almost all engineering disciplines, but the implementation differs widely depending on the manufacturing technology. DFM describes the process of designing or engineering a product in order to facilitate the manufacturing process in order to reduce its manufacturing costs. DFM will allow potential problems to be fixed in the design phase, which is the least expensive place to address them. Other factors may affect the manufacturability, such as the type of raw material, the form of the raw material, dimensional tolerances, and secondary processing such as finishing. Depending on various types of manufacturing processes, there are set guidelines for DFM practices. These DFM guidelines help to precisely define various tolerances, rules and common manufacturing checks related to DFM. While DFM is applicable to the design process, a similar concept called DFSS is also practiced in many organizations. Design for manufacturability for printed circuit boards. In the PCB design process, DFM leads to a set of design guidelines that attempt to ensure manufacturability. By doing so, probable production problems may be addressed during the design stage. Ideally, DFM guidelines take into account the processes and capabilities of the manufacturing industry. Therefore, DFM is constantly evolving. As manufacturing companies evolve and automate more and more stages of the processes, these processes tend to become cheaper. DFM is usually used to reduce these costs. For example, if a process may be done automatically by machines, such process is likely to be cheaper than doing so by hand. Design for manufacturability for integrated circuits. Achieving high-yielding designs in the state-of-the-art VLSI technology has become an extremely challenging task due to the miniaturization as well as the complexity of leading-edge products. The design methodology called Design for Manufacturability includes a set of techniques to modify the design of integrated circuits in order to make them more manufacturable, that is, to improve their functional yield, parametric yield, or their reliability. Background. Traditionally, in the pre-nanometer era, DFM consisted of a set of different methodologies trying to enforce some soft design rules regarding the shapes and polygons of the physical layout of an integrated circuit. These DFM methodologies worked primarily at the full chip level. Additionally, worst-case simulations at different levels of abstraction were applied to minimize the impact of process variations on performance and other types of parametric yield loss. All these different types of worst-case simulations were essentially based on a base set of worst-case SPICE device parameter files that were intended to represent the variability of transistor performance over the full range of variation in a fabrication process. Taxonomy of yield loss mechanisms. The most important yield loss models for VLSI ICs can be classified into several categories based on their nature. Functional yield loss is still the dominant factor and is caused by mechanisms such as misprocessing, systematic effects such as printability or planarization problems, and purely random defects. High-performance products may exhibit parametric design marginalities caused by either process fluctuations or environmental factors. The test-related yield losses, which are caused by incorrect testing, can also play a significant role. Techniques. After understanding the causes of yield loss, the next step is to make the design as resistant as possible. Techniques used for this include substituting high-yield cells where permitted by timing, power, and routability. Changing the spacing and width of the interconnect wires, where possible, optimizing the amount of redundancy in internal memories. Substituting fault-tolerant vias in a design where possible. All of these require a detailed understanding of yield loss mechanisms, since these changes trade off against one another. For example, introducing redundant vias will reduce the chance of via problems, but increase the chance of unwanted shorts. Whether this is a good idea, therefore, depends on the details of the yield loss models and the characteristics of the particular design. Design for manufacturability for CNC machining. Material type. The most easily machined types of metals include aluminum, brass, and softer metals. As materials get harder, denser and stronger, such as steel, stainless steel, titanium, and exotic alloys, they become much harder to machine and take much longer, thus being less manufacturable. Most types of plastic are easy to machine, although additions of fiberglass or carbon fiber can reduce the machinability. Plastics that are particularly soft and gummy may have machinability problems of their own. Material form equals, metals come in all forms. In the case of aluminum as an example, bar stock and plate are the two most common forms from which machine parts are made. The size and shape of the component may determine which form of material must be used. It is common for engineering drawings to specify one form over the other. Bar stock is generally close to 1/2 of the cost of plate on a per-pound basis. So although the material form isn't directly related to the geometry of the component, cost can be removed at the design stage by specifying the least expensive form of the material. Tolerances equals, a significant contributing factor to the cost of a machined component is the geometric tolerance to which the features must be made. The tighter the tolerance required, the more expensive the component will be to machine. When designing, specify the loosest tolerance that will serve the function of the component. Tolerances must be specified on a feature-by-feature basis. There are creative ways to engineer components with lower tolerances that still perform as well as ones with higher tolerances. Design and shape equals, as machining is a subtractive process, the time to remove the material is a major factor in determining the machining cost. The volume and shape of the material to be removed as well as how fast the tools can be fed will determine the machining time. When using milling cutters, the strength and stiffness of the tool, which is determined in part by the length to diameter ratio of the tool, will play the largest role in determining that speed. The shorter the tool is relative to its diameter, the faster it can be fed through the material. A ratio of 3:1 or under is optimum. If that ratio cannot be achieved, a solution like this depicted here can be used. For holes, the length to diameter ratio of the tools are less critical, but should still be kept under 10:1. There are many other types of features which are more or less expensive to machine. Generally, chamfers cost less to machine than radii on outer horizontal edges. Undercuts are more expensive to machine. Features that require smaller tools, regardless of L/D ratio, are more expensive. Designed for additive manufacturing, additive manufacturing broadens the ability of a designer to optimize the design to save materials, for example. Thus, designs tailored for additive manufacturing are sometimes very different from designs tailored for machining or forming manufacturing operations. In addition, due to some size constraints of additive manufacturing machines, sometimes the related bigger designs are split into smaller sections with self-assembly features or fasteners locators. See also, electronic design automation, reliability engineering, Six Sigma, statistical process control, ISQED, DFM in other areas, designed for assembly, design for X. References. Sources: Mentor Graphics, DFM, What is it and what will it do? Mentor Graphics, DFM, Magic Bullet or Marketing Hype. Electronic Design Automation for Integrated Circuits Handbook, by Lavagno, Martin, and Sheffer, ISBN 0-8493-3096-3, a survey of the field of EDA. The above summary was derived, with permission, from Volume 2, Chapter 19, Design for Manufacturability in the Nanometer Era, by Nicola Dragone, Carlo Guardiani, and Anzej J. Stroges. Design for Manufacturability and Statistical Design, A Constructive Approach, by Michael Olshansky, Sani Nassif, Dwayne Boning, ISBN 0-387-30928-4, Estimating Space ASICs Using CIRICH, by Robert C. Sneros, T. Calote Research, Incorporated. Complete presentation. External links: Why DFM is business critical, Design for Manufacturing Checklist to Euro DFM, DFA Designed for Assembly Checklist from QuickTech PCB Manufacturer, ARC Design for Manufacturability Tips, DFM Concept Explained, Design for Manufacturing and Assembly, Turning Designs into Reality, The manufacturability paradigm, list of DFM links.